Well,
or that was the foxhole one.
That was the foxhole
Yeah.
one. But
All right, everybody, welcome out there. You're watching Amateur Radio Roundtable. I'm Tom Medlin, W5KUB. It's all about ham radio. And if you're listening out there on international shortwave, on famous WBCQ out of Monticello, Maine, this show is all about ham radio. So sit back and enjoy. Hey, we'd like to hear from you if you're listening on shortwave out there. Give us an email. Send an email to us to tom@w5kub.com, tom@w5kub.com, and let us know where you are in the world and if you heard the station and so forth. And would just love to hear from you. And also just let you know that if you have internet access wherever you are, you can watch this show live and participate in it through our chat room, but just by going to w5kub.com. Every Tuesday at 9 p.m. Eastern Time. That would be 0100 UTC Wednesday. 0100 UTC Wednesday is our live video show, and you can tune in and watch it if you have internet access, and would be glad to have you there. I'm really interested to hear from people on WBCQ. If you're out there listening on shortwave, we've changed frequencies to 7490. We're on a much bigger, higher power transmitter now. It's getting out around the world quite well now, and you can listen to this show on Thursdays between 5 and 7 p.m. This show repeats between 5 and 7 p.m. on Thursdays on 7490 kilohertz, not kilocycles like the old days, but kilohertz now. So, again, it's all about ham radio. We want to invite you to stick around and join us here. Hey, we got a special guest in the chat room tonight. Michael Coulter, W8CI, is in there. Talk about somebody busy in ham radio. That guy is busy. Michael and I have talked a couple years about him having a segment on this show about DX or international ham radio activity, and he's so busy, it's hard for him to get on here. But one of these days, we're going to talk Michael into being a part of the show. Can't wait. What am I missing here? Let's go around the room here and see who all is with us tonight. We kind of got a small crew tonight, but we're going to have an interesting show. We're going to talk tonight about the 120th anniversary of the first voice wireless, I guess, transmission. Somebody you might not even know. It's a name you might not know. So we're going to talk about that tonight, and let's go over. Let's pick Glenn up real quick and see what Glenn's got going. Glenn, how you doing tonight, man? Down in Mississippi, and how much snow did you get?
I think we got 2 flakes, which shut half the town down.
Yeah.
I don't think it was much this time around, but that's kind of a sign that we may have a bunch this winter. I live on a little bit of a hill, and I need to set the video camera up outside because people cannot get up this hill when it ices up. But boy, do they try. And trees and mailboxes don't stand a chance.
Well,
so.
You know, I knew you got it. You're not too far from me, and we got 3 or 4 snowflakes down here this morning, and it was tough going. Let me tell you, tough going, man. Well, all right. Well, you look like you're starting to relax a little more. I know you're probably getting a little close to finishing your book up.
Getting real close. I've got I was saying earlier on the pre-show, I'm down to one last project to write up that I should finish in the morning, and then I've got a little bit left. And so, I mean, we're on target. Everybody's happy, so it's looking good at this point.
All right. Well, great. Let's see, Alan. Alan, are you there?
I am here.
There he is. Look at that.
Afternoon.
Look, I love
There.
that. Oh, wait, you're not Katie. You're Alan.
Oh, I'm not Katie.
There we
No.
go. That was my mistake.
We can put Katie's picture up. People probably
That's
rather
right.
see
That's
that.
right. All right. Hey, I love the background. You
Yeah,
gonna be
well,
talking about Smith charts tonight?
I'm going to be trying to demystify the Smith chart. Oh, my finger's disappearing when I go off my shoulder there. There we go. I'm going to try to demystify the Smith chart here tonight.
I hope so.
And I mean, it's something that everybody looks at, and just kind of like S parameters. People get, oh, I don't know what that is. It's confusing or whatever. But at the heart of it, in terms of what you see on a Smith chart, is actually comes down to something pretty simple. So we'll try to demystify the Smith chart for everybody. So everyone who's playing with these little nano VNAs that we talked about a couple weeks ago will know what that Smith chart means. So that's what we're going to chat about tonight.
All right. Well, that sounds really good. And a little later tonight in the show, we're going to talk about some of the balloons again. You know, our last balloon went down. We were trying to break our record of 3 times around the Earth, 72 days, but we failed again. But we're going to launch again Saturday, and we're going to talk a little about that launch of our next balloon, which will be called W5KUB-22. We'll talk a little about that. I want to talk a little, and it kind of ties into our first segment tonight. I want to talk a little later in the show about EME. For the show, I want to do some moon bounce and show you that we can set up and make a contact bouncing off the moon with relatively small equipment, maybe a single beam and 70 to 100 watts maybe in a digital mode. We want to show that. So anyway, hey, let's jump right into it with our special guest tonight. We've got with us Bill Mims, W2 at WCM. How you doing, Bill?
I'm doing real well. Thanks a lot, Tom. Thanks for having me, and I'm glad to be here.
Well, I'm so glad to have you guys on, and you're with the Vienna Wireless Society out there, right?
Yep, that's right.
And
I'm a member
you
of
know,
the Vienna Wireless Society, and excuse me, and we're the ones that are sponsoring a special event later on this month to talk about the first voice transmission by wireless radio.
well, you know, and you and I hooked up through Michael Coulter here. Michael, I think, forwarded me your note, and we hooked up here. And I'm glad Michael sent me that note. In fact, I didn't realize it's the same group, but I'm going to be speaking at your Vienna Wireless Society in about 3 or 4 weeks, I guess, in January. I'm going to be talking about pico balloons and whatever you guys want to talk about there. So that's cool.
Yeah, we're looking forward to that, and we're going to be honored to have you there. We also had, let me say hello to Michael. I'm glad he's here tonight. Michael's a good friend, and I remain hopefully optimistic about Hamvention this year. So I'm glad that Michael is part of the team to bring that, hopefully bring Hamvention into operation this year. And as far as the Vienna Wireless Society is concerned, we are really looking forward to hearing from you, Tom. We have several people who are interested in balloon launches, and I told you this earlier, but I'll just say quickly that a few years ago, our club launched several balloons, not pico balloons, but much larger balloons with heavier payloads. And the problem that we ran into was one of our launches ended up taking off right through the approach path to Washington National Airport. So that pretty much ended our balloon adventure.
So that is why you haven't had any more launches in the last 10 years. Is that right?
Right. Yeah. It's been almost 10 years. Yeah.
Oh, wow. Well,
so we're going to learn a little bit more about balloon launches from you, and hopefully we can do a better job with our next one.
Well, you were really flying in some restricted airspace, let me tell you. We have a friend that teaches school, and they're wanting to put some balloons up, but they're limited to 1,000 feet tethered. They cannot launch. So, hey, that rule may have come in because of what you guys did. I don't know.
Yeah.
Well,
they
look,
may have
hey,
done-
hey, let's talk a minute about, well, more than a minute. Let's talk about this 120th anniversary here, and what's going on and what you guys are planning.
Okay. Well, first, just let me tell you how this came about. Our club is a pretty active club. We have over 250 members, and we have several nets, local and otherwise, each week. And on one of our nets, we have a tradition of asking amateur radio trivia type questions. And a few weeks ago, one of our members was net control, and she asked the question, when was the first transmission of voice by wireless? And it turns out it was on December 23rd, 1900, and it was done by this gentleman, Reginald Fessenden. And I'll tell you just a bit more about him in a minute. And then it struck us that as the club is always looking for some fun activities, and we do special events from time to time. We hadn't done one in a couple of years.
Oh, this is interesting. Bill, you froze on us. Let's see if Alan.
I hear you. I still hear you.
We're
Tom,
still working,
so-
right? Okay.
Yeah, so it looks like Bill froze on us there.
Yeah, it looks like he might have had a slight internet problem, but I'm sure it will recover here in a minute. Well, let's give it a second. Bill, are you hearing us now? Well, I don't hear Bill. And he's not moving. I'm seeing him there, but he looks frozen.
That's not a good sign.
Yeah, well, we're going to get through this regardless.
Looks like he's going to try. Looks like he popped off. I guess he's going to try to rejoin.
He'll reconnect here. So in the meantime,
he's coming back.
Well, here he comes. He's coming back now. He's got headphones on this time.
All right.
Hey, Bill, how you can you hear us, Bill?
Yes, I could hear you throughout that whole thing. Can you hear me?
Yeah. Well, yeah.
Yep,
yeah.
got you back.
Oh, you got a good signal now, man. You're coming in 30 over S9 now. You're doing good.
Okay. Well,
Do you remember where we were?
No, tell me where I cut out.
Well,
It said you were just about. You're always looking for some special events, and that's about kind of when you froze.
Okay. So this is we decided to do this to celebrate this event because it occurred just a few miles south of here on Cobb Island in the Potomac River. And essentially what happened was Reginald Fessenden was a sort of a Renaissance guy. He was involved in lots of different endeavors and did a lot of work in radio and radio telecommunications. In fact, he was the guy that first used a carbon microphone to modulate a carrier signal, and so he's really the father of amplitude modulation. I could go on about him, but let me just say that what happened on December 23rd, 1900 was he set up a couple of antennas about a mile apart on Cobb Island, and he used a sort of a makeshift rotating spark generator to generate essentially a steady wave, and he modulated that wave with his voice. And it was received and heard a mile away. So that meant that was the first time that voice transmission was carried over a wireless system. So since that was 120 years ago, this coming December 23rd, we thought it was a great opportunity to have a special event. And that's what led us to this point. I hope that was understandable.
Yeah. And you know what amazes me? I've been licensed almost 60 years. I go back pretty close to this. It's kind of scary thinking that it wasn't that many years before I got my license that.
You're halfway down there.
Yeah, wasn't that many years before I got my license that we didn't have good radio.
Yeah.
Man.
There you go. So I could tell you more about Reginald Fessenden, but he was quite a guy who developed a number of other important radio-related. There you go. There's his biography. A couple of other radio-related inventions. In fact, he developed an oscillator, which was called originally the Fessenden oscillator, which was the basis of sonar, which was used by the Navy, especially in the submarine warfare. So there you go. That's a little bit of the story of Fessenden. He was quite a guy. He ended up, he never actually got a degree from a university, but he taught at 2 universities. He was a professor of electrical engineering at Purdue University, and he was head of the department at what became Pittsburgh University. So without a whole lot of formal education, as a sort of a self-taught guy, he ended up being quite a factor in the early days of electrical engineering.
Yeah. Now we can. This link was off of your Vienna Wireless Society homepage. If anybody wants to check this out a little later, let me go back here. There's your there's you guys' homepage for the Vienna Wireless. It's just viennawireless.net, and there's a link here to this event. Hey, you're going to send out some QSL cards and stuff, right? Let's see.
Yep.
Y'all got some nice cards made up. Here we go.
Yep, that's the front of the card. A little map showing where Cobb Island is. And that marker is located on Cobb Island, not far from the spot where he did this feat.
How close to that spot are you going to be operating?
Well, we have one guy. In fact, it was interesting when you flashed by a picture of a red Jeep on our webpage there. We call that the Mad Max. We have one member who is a UHF VHF contester, and that Jeep has an amazing set of antennas on it. And he's going to take that thing to Cobb Island sometime during the week and operate VHF, UHF, in every mode he can. So hopefully we'll be very close to the spot where this actually happened.
Nice.
So Bill, this people, and when is this event going to happen? What period?
Okay, thank you for asking. That's a great question. Starting on December 18th through the 24th, we will finish up at midnight Greenwich, which would be 7 p.m. local time on the 24th. And I'm glad you brought up the webpage, because that's where you can find out when someone will be on the air. We're going to try and operate on as many modes, as many bands as we can throughout the day in 2-hour blocks. And if you go to our website, viennawireless.net, once once the special event begins, you'll see when people are going to be operating in what mode and what band. So look for us and come help us build up some pileups.
Well, that'll be cool. I'm gonna try to work you guys. So during that time period, and how do you get? If you just work do you have to send a QSL card in to you? Do you have to self-addressed envelope? What do you guys? Any requirements?
Yeah. First of all, we are going to confirm everything via Logbook of the World. But if you want a physical card, we're happy to provide one. There's the back of the card there. All you need to do is send us your request with a self-addressed stamped envelope to that address that's on the bottom of the card there. It's also on the website, and we will send you a card.
Well, that's cool. I'm gonna try to get one, and it'd be interesting working you guys. And as I mentioned earlier in the beginning of the show, I've never heard of this person before, and I thought I was pretty much in radio all my life. But it's interesting to hear stories about people like this.
Yeah, I think so too. And in fact, as I was talking with you earlier, Tom, one of the things that made this an important event for me is that we as amateur radio operators stand on the shoulders of some great people. And a lot of people, as Alan said earlier, have heard of people like Marconi and Heinrich Hertz and Maxwell and those folks. But there's a lot of other people that we owe a debt to who are almost unknown, like this gentleman, Reginald Fessenden. But he was quite a guy. So we hope we hope a lot of people will join in celebrating one of his first accomplishments. By the way, he was also the guy that made the first radio broadcast just a few years later on Christmas Eve, 1906, from a station he had put up in Maine. He broadcast to several ships at sea some Christmas music, including a violin solo where he played the violin.
Okay, so everything prior to this basically was CW, and so you've got these receivers out there on these ships, and all of a sudden they're hearing music out there.
Right.
That was probably a really exciting thing to hear for the first time.
I can imagine so. I've read
Yeah.
a little bit about some comments that people said that they were, there they were on Christmas Eve, and all of a sudden they heard music
Yeah.
on the radio.
Oh, wow. Well, your group was also involved in, Alan, tell me again, what was the name? Operation, the EME stuff.
Well, the one that we did. Yeah, so kind of going back in history again, also, you had mentioned last week, and maybe you're going to talk about later on, wanting to get into doing some moon bounce.
Mhm.
And kind of along the lines of what Bill's talking about, I got involved with one of the clubs I'm with, that I'm a member of, for the 70th anniversary of Project Diana.
Yeah.
Project Diana was a project that was run by the U.S. Army Signal Corps in 1946, where they first bounced a radio signal off the moon. And it was done here in New Jersey at Camp Evans, which used to be part of Fort Monmouth. And actually, the club I belonged to, their building was in Camp Evans, about 20 feet from where this antenna was that was used for Project Diana. So we actually had a special event 70 years
Okay.
later to the minute. We can talk about later on.
So I think I confused that with the Vienna Wireless.
I'm sorry.
It was a
I'm
different.
sorry.
It was a different group that did that special event there, right? I mean, in fact, it's been a few years. I had them on the show here when we had that 70th anniversary, and we had pictures of the buildings, and I forget who was on here with us. I'll have to go back and look at that. Let's jump back here again to Vienna Wireless here, and see if there's any questions out there in the chat room, or anybody want to ask a question. I think it's pretty clear that this is going to be a great special event, and it's coming up soon, December 18th through the 24th. That's just a little over a couple weeks away.
Correct. Yeah, I'll be happy to answer questions if there are any.
Yeah, I'm looking for. You said you're going to work. I was trying to think from where you guys are down there. Probably 40 or 75 would work great here to New Jersey. So hopefully you'll be on those bands. I'll try to look for you there.
Yeah, we do. We plan to be on. We actually hope to work all the amateur radio bands, including the work bands, up to 2 meters. And we're going to operate primarily CW sideband and FT8, although we are going to have some slots reserved for AM because of Fessenden. He was the father of amplitude modulation, so we thought it would be fun to have some AM thrown in there as well. So if you're an AMer or even want to try it, this might be an opportunity.
Well, you just answered a question in the chat room. What modes? You're going to try to do a lot of modes. Yeah.
Primarily CW, sideband, and FT8, although we do have some members who are going to operate, or I think are going to operate PSK 31, and we do plan to operate AM, as I said.
Yeah, and there's another question. What equipment did Fessenden use for the transmitter? I'm not sure that it even had a model number. Probably homebrew, I guess.
It was a homebrew. I am probably not the best person to answer that because I'm not really a very technical guy, but my understanding is he had developed a system to create a rotating spark generator because he was trying to generate a continuous wave. He was already to the point where he said, we need to stop this on and off stuff and generate a continuous wave because we can do so much more with it. And that was what happened. He was able to use a rotating spark generator and generate something approximating a continuous wave, which you then modulated.
Well, here's a comment from David in the chat room. Radio Canada International commented that one ship operator said he heard the voice of an angel. Well, I don't know. Maybe that was part of this. I don't know.
Well, he did play some music, some recorded music, and I'm not sure what that was. It might have been a female voice that sounded like an angel.
Yeah, it could have been. Oh, man. Oh, All right. Well, look, hey, man, thanks so much for bringing this to us. Hey, how can people, if they need to get in touch with you, how's the best way for them to get in touch with you?
Please send your comments, questions, suggestions, requests, whatever to me. And you can reach me in my call sign at awrl.net. That's Whiskey 2, Whiskey Charlie Mike at awrl.net. And I'll be glad to get back to you as soon as possible. We invite everybody to join us. We hope you have some big pileups. And we appreciate the opportunity to be here on the Roundtable. You have developed quite a program here, Tom, and I'm honored to be part of it. Thank you for allowing us to be on.
Thank you for being with us tonight, and we hope to get the message out about this. And hey, besides our show tonight, it's going to be on the shortwave. It's also going to be on our podcast that people download, and it's going to be all over Facebook. So it's amazing how we have so many different outlets now to get the word out about things like this.
Yeah,
all right, man.
You're lucky.
Well, thanks so much, and feel free to stay with us tonight. And if there's anything coming up and you want to jump in and talk about it or comment, please do.
Well, I appreciate that. I'm going to stick around because I want to hear Alan explain what a Smith chart is.
Yeah, and I do too. I need to learn it. Boy, I think it scares me when I look at that Smith chart. I just kind of, I try not to use it. In fact, I got a VNA over here, and I need to turn it off so I don't see it. I don't know. Anyway. All right, hey, we'll be back in just 1 minute, guys. Everybody stand by with us. Be right back. Ham for the holidays. ICOM's new ID52A and the IC705 give hours of fun and enjoyment working your favorite bands this holiday season. ICOM's newest handheld amateur radio is the ID52A. Larger radio, larger color display, and a louder audio. This VHF-UHF digital receiver is much more than a replacement for the ID51A. It's also a new way of communicating. The multifunction D-band D-Star transceiver supports DR mode for easy access to local repeaters based on internal GPS information. The ID52A also has Bluetooth for audio and data control. And for the first time in the amateur radio industry, you can now send photos from a connected Android device. Other features include wideband receiver with guaranteed range of 144 to 148 and 440 to 450 megahertz, integrated GPS including grid square location, the micro USB for data transfer, programming, and charge, and it's IPX7 waterproof. The ID52A is a perfect companion to the IC705. Both use compatible batteries and headsets. And you can also use the same Android app for D-Star operation. The IC705 is a perfect sidekick for hams that like to enjoy both the indoors and outdoors. It's the perfect QRP companion and covers HF 6 meters, 2 meters, and 70 centimeters. This compact rig weighs in at about just 2 pounds. It has a 4.3-inch touch screen with live band scope and waterfall, and you get 5 watts with the BP272, and you get 10 watts with the 13.8 volt DC. It has a micro USB connector, Bluetooth, and WLAN, integrated GPS with antenna and GPS logger, and it comes with a speaker microphone standard. The perfect accessory for the IC705 is the optional LC192 backpack. It has a special compartment for all of your accessories. Visit www.icomamerica.com/amateur for more information on ICOM radios.
LDG Electronics amateur need. From QRP to QRO, fixed stations, portable and remote, an LDG tuner will match your radio to your antenna using our lightning-fast proprietary tuning algorithms. LDG is a family-owned and operated company dedicated to bringing innovative, quality products to the amateur market. All LDG products carry a full 2-year warranty that is fully transferable. Support is only a phone call or email away. We're always here to help you. Visit us on the web at ldgelectronics.com.
Got too many
Okay,
screen
guys,
hosts.
sorry. We had a mouse problem. The mouse did not want to go where we were telling it to go. We couldn't get the show back on track here. I am so sorry about that. I'm going to have to work on that mouse. All right. Well, hey, Alan is going to talk a little about Smith charts, and he's going to try to make it easy for us to understand. And for me to understand it, he's going to have to make it real easy. So, Alan, go ahead and pick it up, man, and let's see what you can do as far as explaining this to me, okay?
Demystify. Well, it's funny, you were talking about the mouse problem. It reminded me of those Geico commercials. You know, we got a clogging problem. You got those guys clogging upstairs in the house.
Yeah, I've seen that. Uh-huh. Yeah.
You got a mouse problem. Okay. Yeah, so let me share my screen here. Again, what I hope to do is just to demystify the Smith chart here, and we'll do it. I've got this is a presentation that I gave to a local VHF radio club, a radio organization here a few years ago. I'm not going to go through the whole thing because it goes into some impedance matching, which we don't have to talk about unless people want to. But I figure we'll start here, and we'll just kind of start with demystifying it. So the first part is, what is a Smith chart? It's a graphical tool to plot and compute things like complex impedance. That's oftentimes that's kind of what it shows directly. But in addition to that, complex reflection coefficient, we won't spend too much time talking about that. We'll certainly spend some time talking about SWR, because that's what most of us as hams, the first thing that we want to do when we start looking at antennas and things like that is to look at SWR. That's one of the things you can visualize on a Smith chart. We also can talk about transmission line effects and show what happens with different transmission line lengths, and we'll talk a little bit about that as well as being able to help you design matching networks, either at the antenna or at the transmitter or both, and a whole lot more that we won't even get into. But it's really a bit of graphical magic that does all of this. Let's just break this down and try to simplify things a little bit, and hopefully you take one or two nuggets away from this to understand what a Smith chart is, and that's all I'm intending to do here. So let's talk about what we call the regions on a Smith chart, the impedance regions on a Smith chart, because at the end of the day, the Smith chart is representing complex impedance. Now, the horizontal line that goes right through the center represents purely resistive impedance. Okay, basically, essentially resonance, because resonance is defined where the reactance is equal to 0. Now, on the Smith chart, that is represented anywhere along that horizontal line. Okay, and that's where complex impedance is purely resistive with no reactive component at all. Any plots or curves or points on a Smith chart that are above the line in the upper hemisphere, if you will, are regions of impedance that have got a resistive component and an inductive reactive component, right? And then conversely, the lower hemisphere is where you've got a resistive component potentially and a capacitive reactive component. So that's kind of the regions of the Smith chart. So if you're ever looking at a curve and things like that, you can point at a particular spot and say, my antenna is slightly inductive at this frequency, it's slightly capacitive at that frequency. Okay, and that's just kind of where the regions are. And then anytime your curve crosses through the equator, if you will, that's where your inductive and your inductive and capacitive reactive components go to 0. Which kind of defines resonance. Remember, resonance doesn't always mean 50 ohms. It just means that the reactive component is 0. Because that's not where those things are represented on the Smith chart. So we'll ignore a lot of the other numbers and circular dials here for the moment, but at the end of the day, that's really how complex impedance is plotted on the Smith chart. We'll get a little more detail on that as we move forward. Now, what are some of the key values or key locations on the Smith chart? Well, right in the center, right in the bullseye, is essentially our desired system impedance. And most often we just refer to that as essentially, that's our perfect 50 ohms. It doesn't have to be 50. The Smith chart is designed to be used for any system impedance. It could be used for It was originally developed for doing some work on long telephone lines that had a much higher impedance, and you can normalize the chart so that that system impedance is what appears in the center. But for us working in RF, the vast majority of the time that our system impedance is 50 ohms, and that's represented right in the dead center of the chart, right in the bullseye. Okay. And if you've ever ran a calibration on your nano VNA, like we talked about a couple of weeks ago, when you put that 50 ohm load on there, the Smith chart goes right to the center. Okay. Now, all the way over in the 3 o'clock position, that represents an open circuit. Okay, so an open circuit impedance, infinite impedance, is shown right there at the 3 o'clock position, and conversely, the short circuit position is all the way over at the 9 o'clock position. So those are some key values on the chart. So we go to higher and higher impedance as we move to the right, lower and lower impedance as we move over to the left. Okay, and then our perfect 50 ohm system impedance is right there in the center. So we can keep some of that in mind here as well. And again, if you're playing with your nano VNA and you run through your open, short, and load calibrations, you'll see that the open, the short, and the 50 ohm load will essentially put traces or plots, curves, marks on the Smith chart in those locations. Okay. So one thing we'll have to talk about is something called normalized impedance. Because the Smith chart is designed to be operated at, or to be used at whatever your system impedance is, in order to plot something on it, we have to normalize that impedance to the system impedance. And all that means is that we take the actual complex impedance and divide it by our system impedance. So for example, in our case, if we have a system impedance of 50 ohms, we simply just divide those complex impedance values by 50. So for example, if you had an antenna analyzer and it said that your antenna impedance or the input impedance to your amplifier or into the coax feeding an antenna is, say, 37 plus J55 ohms, meaning 37 ohm resistive plus 55 ohms of inductive reactance, we would normalize that by essentially taking those two numbers, dividing them by 50, okay, and we'll delineate the normalized impedance by putting the little prime symbol next to it, so it says Z prime. Therefore, the normalized impedance in this case would be 0.74 plus J 1.1. Okay, that's all it is. It's just simply dividing those complex numbers by 50 to normalize them. And this makes that chart, the Smith chart, usable for any system impedance. Okay, and this normalized impedance is what we plot on the Smith chart, and that's what you'll see. For the Smith charts that you see on an antenna analyzer, sometimes they'll show the actual impedances or the graphs. The Smith chart itself might be what will show 50 ohms instead of the normalized thing. But if you pick up any paper Smith charts, the center of the chart will be 1, right? Because that's 50 ohms divided by 50 is 1, right? So the center of the chart is 1. Everything is normalized. But that's what when you look at it, that's why the numbers don't look like what you might expect off your antenna analyzer, because they're typically normalized to that system impedance. So on the Smith chart, what are all these circles and arcs and things like that? What are all these lines? So all of these circles that you see that kind of all are tangent to the 3 o'clock position are what are called constant resistance circles. So each of those corresponds to a normalized resistance of some value. The circle that kind of touches the 3 o'clock position and goes through the bullseye and dead center is the normalized resistance of 1. And then, for example, this one that's the normalized resistance of 3. That would be like 150 ohm, for example. The big one right there is it would be 50 ohms. There's a normalized resistance of 0.4. Okay, so that would be 20 ohms. Okay, and so on. And if you take a look at the chart, right in the center, you'll see these little red numbers. Let me grab my mouse here and throw a laser pointer on there. So you can see these red numbers here. These are the normalized resistance values, okay, associated with all of those circles. So you can see 1 right here. That is actually this 1 that's right there, and that's kind of right against that normalized resistance circle of 1. Okay, so all these little red numbers associated with those circles will tell you what those constant resistance values are. Now, the arcs that you see that are emanating from the 3 o'clock position, these are our constant reactance arcs. So I've kind of indicated here a constant inductive reactance of 1, plus 1, and a constant capacitive reactance of minus J.1. And similarly, you'll see these little red numbers along the perimeter of the dial face here. There's a 1 right there. This is 1.2. This is 1.4, etc. So, for example, this is the 0.5 set of arcs for inductive and capacitive reactance. Again, those numbers are all off onto the side right here in the same color as the arc itself. So you have these constant resistance arcs, constant reactance arcs, and then obviously the intersection of those is essentially how you plot complex impedance. Okay. Again, this all flattens out to when you have no reactance at all. These curves flatten out, and no reactance is again the equator going right through the center. Okay. That's kind of how complex impedance is represented on the chart. So wherever you've got a point or a trace that shows you how that impedance is varying versus frequency or whatever it is you're varying, that's causing that arc to happen. Okay. So here's how we would go ahead and plot a complex impedance, right? So let's say I had this complex impedance of 25 plus J40, so 25 ohms plus J40, which is an inductive reactance. So the first thing we do is divide by 50 to normalize the value. And that would give us the normalized impedance of 0.5 plus J.8. What we do is we locate those two arcs. So in this case, we want to find the constant resistance arc circle for 0.5. So there it is right here. Okay. And then we find the constant reactance arc of plus 0.8. So that's that guy right up there. And then we follow those two curves down. And where they intersect, that point right here is the plot of that particular complex impedance on the Smith chart. That's as simple as that. That's really kind of how the Smith chart, shows you what a complex impedance is. And obviously, when you're sweeping an antenna, for example, you don't see a point. You see a trace. You see a curve of some sort. And we'll talk about that as we move forward. But the curve just kind of shows you how the impedance varies versus that frequency sweep. Okay. So, and ideally, we want that curve to kind of sweep right through our bullseye, at our desired operating frequency. So, a couple more things that you can see on a Smith chart. Let's say I've got a complex impedance that's plotted right here. Okay, in this case, it's got, it's about 0.55 on the resistance side, and then the inductive side, or actually in this case, capacitive side, we're around 0.45 or something. Okay. There are a number of other scales on the Smith chart that we call radially scaled parameters, and what that means is we take a line from the bullseye out to where that complex impedance is, and we call that kind of the radius of a circle that you could draw around here. But if we take that radius and we arc it around, okay, and rotate it back up to the equator, if you will, the prime axis here, all right, and then extend the line down from that down to the radially scaled parameters. We have a number of different parameters that we can read off that will tell us something about that impedance. So there's the first scale right here, it says right on it, SWR. Okay, so in this case, this complex impedance, as we rotate up and slide down, okay, that is essentially that's this distance from the center here. Okay, it's the same distance. We can read off the SWR in this case is 2.3 to 1. So right there's 2 and there's 2.5, so there's 2.3 to 1. We just read off the SWR. So we know just from looking at this Smith chart, the distance from the center is proportional to SWR, right? If we were perfectly at the center, right, we'd be right at a 1-to-1 SWR. The further we are from center, right, the longer that radius or that the the more the SWR goes up. There's 1.5 to 1, 2 to 1, 3 to 1, etc. So the further away you get from the center is the higher the SWR is. Similarly, the return loss, which is another way of expressing return loss or reflection coefficient, they're expressed here as well. So we've got SWR, we've got return loss in dB. In this case, it's 8.1 dB, so 2.3 to 1 SWR gives you an 8.1 dB return loss. Our power reflection coefficient is 0.155. It's on this scale down here, reflection coefficient for power. And then the voltage reflection coefficient, voltage or current reflection coefficient is down on the bottom scale. But the two that you use probably most often would be maybe the SWR and the return loss in dB. Very simple to figure that out by looking at the Smith chart. And like I said, the end of the day, is the closer you are to center, the lower it is. Okay, but that's how you read SWR off a Smith chart. So let's talk a little bit more about SWR and transmission lines and what happens on the Smith chart with that. So if we take and we draw a circle centered at the bullseye around a particular complex impedance point like we just described, that all the points on that circle represent the same SWR. So yes, the impedance varies, right? You can see the complex impedance values vary because we're crossing through different arcs and different circles. But anywhere along that line, we have the same SWR because the radius of that is the same, right? We saw in that previous slide, it was really just the radius that determined what the SWR is. So that's kind of an interesting concept. You can have, an infinite variety of complex impedances that give you the same SWR. And that's what's represented by drawing that circle. Now, why am I drawing that circle? Because another way to think about this is that one trip around this circle represents a half wavelength of transmission line length. Okay, let me say that again. One trip around the circle represents one half wavelength of transmission line length. So let's say I was operating at a particular frequency, and my SWR, I measure my SWR and I measure my complex impedance. If I add exactly a half wavelength of transmission line length to my transmission line, and let's assume I had no loss in the line, I would have exactly the same impedance measured again. Okay. Now, so the impedance repeats itself every time you have a half wavelength of additional length or less length. So every even quarter wavelength, multiple, or in other words, every time we have a half wavelength multiple of wavelength in transmission line, the impedance repeats itself. Okay. Now, halfway around the Smith chart, obviously, then is a quarter wavelength. Now, some interesting things happen at a quarter wavelength. The impedance actually kind of inverts. So if we think about it, if we get halfway around, we come out over here. Still the same SWR, but now our impedance is it inverts around the system impedance. So one of the extremes to look at, which is kind of interesting, is let's say I have a transmission line that is open at the far end. Okay, say it's open right here. Now, if that transmission line is exactly a quarter wavelength long at the frequency I'm testing it at, it's going to look like a short, even though it's open at the far end. And this is the concept of like stub filters. Okay, so sometimes you hear using a transmission line stub as a filter. If you take a transmission line that just happens to be a quarter wavelength long at a particular frequency, and you leave it open at the far end, it looks like a dead short at that frequency, looking at the near end of that coax. And similarly, if I've got a piece of coax that's shorted at the far end, okay, and then I go a quarter wavelength further down that line and then look into that line at that frequency, it looks like an open. So kind of interesting. And this is used all the time for various impedance matching things, as well as developing filters and things like that. This impedance transformation that you get because of this quarter wavelength line. So kind of interesting. And like I said, this is kind of just the basics of this. If you want some time here, I can get into just the basics of how you use some of the Smith chart to do to develop matching networks like an L network. Just a couple more slides. What do you think, Tom? We want to go through that too?
Yeah, we can spend a few more minutes on it.
Okay, yeah. So let's go through it. Like I said,
I'm interested. I like to build a lot of LC networks for matching.
yeah, that's exactly what this is going to talk about.
Yeah.
And this is all in the video that's on my channel too. But I figured sometimes it's nicer to talk through it. So let's talk a little bit more about the transmission lines here. Now, one thing with the transmission lines here is this allows you to predict the impedance at different line lengths. And what I mean by that is, let's say we look at these scales on the outer edge. We see the scale that says wavelengths towards the generator and wavelengths towards the load. What this allows us to do is to make a measurement, say, at the transmit end of the coax, and then predict what the impedance actually is at the antenna. Okay? Because as we said, as we move around, this is just like changing the length of transmission line. That's why sometimes if you add or remove transmission line length, that sometimes your antenna, your automatic antenna tuner might work better. It's not because it changes the SWR. It just changes the ratio of real to reactive components to a point where maybe your tuner's a little happier to deal with it. Okay, so it's not really changing the SWR. It's just changing the impedance that's seen, and might make it happier. Now, let's say for example, I put an antenna up in the air. It doesn't have a great match on it, and I can only measure it at the transmit end. But I want to design a matching network that I put at the feed point of the antenna. So what I can do is measure that my complex impedance at the transmit end, and then if I know the length of the antenna or the length of the coax, I can say rotate in this direction towards the load and rotate this way and actually predict what the impedance is at the antenna feed point. Once I know the impedance at the feed point of the antenna, I can design a matching network for that particular impedance, put it at the feed point, and then the transmission line always sees 50 ohms. Because that's typically why you go ahead and do that. Okay. So a typical antenna plot you might have on a Smith chart might look like this. Okay. Just a plot of complex impedance versus frequency. Okay. The ideal matching point right here. So at this particular frequency, whatever it was, that's where I had, would have a perfect 50 ohm match. SWR would be really good. Return loss would be really low. Okay. Again, the radial distance from the center to any point on the curve will tell you what the SWR is at that particular point in frequency. Okay. And then the shape of the curve and whether it loops around or just arcs or something like that is going to depend on the antenna, the feed line, the frequency range you're making the measurements over. So you can get some really screwy looking curves, but this is pretty common. And you'll note that we actually crossed through the resistance axis here 4 times. So there's actually 4 resonant points for this antenna. But these two certainly have got a very high SWR. So again, resonance only means that the reactance is 0. It doesn't mean that's where you're going to have a minimum SWR. In this case, I happen to draw this so that we have a resonant point right at my 50 ohm point. I've got another resonant point right here that would be as just pure resistance. It would probably give me about a 1.8 to 1 SWR or so at that point. But then I've got other points here. This would actually be a lower SWR here. It just means it's got a little capacitive reactance or a little bit of inductive reactance. Okay. Again, the closer you are to center, the lower your SWR will be. Okay. And typically on this type of a chart that you see on an antenna plot is not going to have any kind of a frequency axis. So you typically will need a marker or some other indicator of what frequency is being represented at a particular point on the curve. That's the only real downside to just looking at a Smith chart by itself, is you can't tell where you are in frequency on that chart. So you really need kind of a marker or a cursor of some sort. So when we want to design an impedance matching network, we can actually use the chart to do that. And typically, when you're doing an impedance match like an L network, you're typically adding series or parallel inductors and capacitors to move from our actual load impedance to the dead center. So the L network topology you use is going to be dependent upon what the load impedance is. And you get these kind of yin-yang diagrams that kind of give you an idea of that. Let's say, for example, if my measured load impedance falls in this area on the Smith chart, okay, then the kind of one of the recommended networks might be a series L and a shunt C in parallel with your load. And then you can see you've got a couple of other diagrams that indicate when you'd use these various other configurations to create your L network. And for some impedances, for example, like let's say my impedance was sitting right up here, I could use either this network or this network, right? Because both of those impedances are kind of indicated there. So really determine which one is going to be desirable might depend on which one gives you more practical values, or whether or not you want a high pass or a low pass network, as part of that L network. So sometimes, again, more than one topology will work, to design a matching network. So let's see what happens on the Smith chart if we're starting to add some of these elements. So I'm going to add elements to kind of move my point down. The idea is, let's say I've got this is my measured complex impedance in my antenna. I really want it to be here. So I need to get there somehow. And the only way to get there is to kind of add these other components. Now, if I add a series inductor or capacitor, I'll move along the constant resistance circles. So adding a series inductor moves me this way on the constant resistance circles. Adding in this case, adding series inductive reactance of J0.6 normalized, okay, will move me along that far along the constant resistance axis. Adding a series capacitor moves me the other way around. Okay, so that's two ways to move along the Smith chart. Okay. Now, when we start adding shunt elements in parallel, then it's handy to talk about admittance instead of impedance. It's just 1 over the impedance, because then we can just talk about adding things again. So the conductance is essentially 1 over the resistance. Susceptance is 1 over the reactance. But the reality is it's not this exactly, because this is a complex number. So you only get these two equations when the real component is 0. So we'll show that on the Smith chart. And converting to impedance and admittance on the Smith chart is super easy. So let's say I've got a complex impedance here. We draw a circle, and then we bisect it. The complex admittance is simply diagonally opposite that. So in this case, what I'm showing here, which is a 1 plus J1.1, the complex admittance is, you can read right off the curves here, 0.5 minus J.5. Okay. Something is binging over here. I'm not sure what it is. Let's see.
Well, we're not hearing it.
Okay, all right, well, I'll just go back to where I am here. I'll figure out what's binging here afterwards. So the complex admittance curves, if you looked at them, is actually simply taking the Smith chart and rotating it by 180 degrees. Okay. The reality is that a lot of Smith charts you can pick up and use are combination charts, where you've got my pointer back on here again, where essentially you've got two sets of curves. In this case, the red curves are all the ones that we typically talked about. The blue curves are my complex admittance chart, complex for the admittance curves. So there's a constant conductance circle as opposed to a constant resistance circle. And I've got my constant susceptance arcs as opposed to constant inductance arcs, okay, or reactive arcs. So if we add elements in parallel, then we're going to move along the constant conductance circles. So adding parallel inductor, adding a parallel capacitor moves along those constant conductance circles. So again, really easy to do with a combo chart. Okay, in this case, we're just moving around. So a quick tip when adding elements: when we add inductors, okay, when we add series inductors, we move up. We kind of elevate through the real axis. That's where the L comes from for inductors. When we add inductors in parallel, we're typically moving up. Now, the reality is we're adding a parallel susceptance. So as we move up, we're actually going to lower and lower values of inductance. If you think about an extremely large inductor, is going to look like an open circuit, right? So that's like not changing anything at all. As you reduce the inductive value, then we're going to start moving up that curve that way. And if we, for capacitors, we go the other direction. Okay, so it's just a way to kind of remember in your head, if I'm adding capacitors or inductors, which way I'm moving along these curves. We use this to develop a matching network practically. Okay, so here's a quick example. Let's say I've got this complex impedance right here. I want to actually get here. Right? I need to design a matching network to get there. So I look on my little yin-yang diagram and decide that, okay, a shunt capacitor followed by, or excuse me, a series inductor next to the load, then followed by a shunt capacitor is the L network topology that I want to use. So I'll start by adding the series inductor. So I'll add this. Now, what we want to do is get ourselves to the center. And typically the way you're going to do that is you want to rotate one way or the other to get to either the constant, the R equals 1 or the constant conductance of equal to 1. I want to get to one of those two circles so I can rotate back down on that. So in this case, I'm going to add a series inductor that rotates me up onto this constant conductance of 1. Okay, and then I'll add the shunt capacitor that's going to rotate me along the constant conductance circle down to the center. As simple as that. So if I rotate, and you can read off the scales how much inductance and capacitance we've added. Then we'll just compute the values from that. So we'll do one example here. Let's say at a frequency of 432.1 megahertz, I measured 75 minus J60. Okay, we normalize that. Okay, and plot that. Okay, there's my point right here, 1.5 minus J 1.2. Now I want to move that ideally to the center. So if I look at my yin-yang diagram, I'm going to use this topology: a shunt inductor first, and then a series capacitor. Okay, the shunt, we're working from the load out. We'll first go with the shunt inductor, right? So I just highlighted my constant resistance circle here of 1. So I know I want to kind of get there. And remember that a shunt inductor is going to rotate up the constant conductance circle. So I'm going to rotate all the way up that far until I hit R equal 1. Now, if I look at how far I moved, like this is actually the arc of, say, from here to here is 0.32. And then from here to here is 0.5. And we're just reading that off of these scales. So in this case, I went from 0.32, we kind of just barely see that in here, up to here, and then 0.5. Okay. So I moved a total of acceptance of J0.82. So if I invert that, that's normalized inductive reactance of J1.2. So my actual inductive reactions of J61, and then knowing my operating frequency, I can compute that to 22.5 microhenries. So I know my shunt inductor is 22.5 nanohenries. Now I need to move, I want to add I know my capacitor value, now I want to add my series capacitor. Assuming I know my inductor value, I want to add my series capacitor. And again, that's going to rotate me along this circle here, so I just want to go all the way down until I get right to my perfect point. And I can see that I moved from 1.2 down to 0. So I moved down J1.2, or minus J1.2. Denormalize that, so it's a 60 ohms of capacitive reactance. And then from that I can compute the capacitor 6.14 picofarads. So now I have my L matching network that will take that complex impedance that I measured at 432 megahertz and I make it look like 50 ohms looking into it. That's how we do that. So I'm not going to do the extra credit piece of it. We'll just kind of maybe pause there. So, so hopefully that maybe you got a couple of nuggets out of it to understand what a Smith chart is, what the curves represent, and then how, in this case, how it was actually used to do some pretty complex calculations graphically rather than going through all of the numbers. So that's kind of what that was all about.
All right, so let me get on here with you. There we go. So it's still pretty complicated to me. It seems like, though, you got a really good grasp on it. But
Yeah, I mean, like I said, it can get complicated, but at the end of the day, the distance from the center is just and you can adding or subtracting transmission line length is really kind of just.
But I saw a lot of things when you were explaining it. I saw a lot of things. I know in an LC circuit, you can set it up to tune a high impedance, or if it's a low impedance, you turn it around.
Yep.
And
Yep,
I started to see those pieces on that chart as you were talking about it. And it's just amazing how that chart does everything. It's like everything in the electronic RF universe is on that chart.
Yeah.
I mean, it includes about everything.
Yeah, and actually the guy who invented the chart is author of several books. The most popular one is this Electronic Applications of the Smith Chart. This is a later copy of it. This is an earlier copy of it. You can find these sometimes in a library, find them sometimes for sale at a Hamfest.
Yeah.
And so there's a lot of good information that's out there. And but like I said, at least now if you look at your Nano VNA and you see the little curly Q on there, at least you understand where you are and what it's doing and what it's representing.
In fact, that chart does so much. When you had a chart up and you had a little squiggly line around it like that. You remember that?
Yeah.
That chart does so much. It actually plotted the route of our last balloon launch over the Philippines. And it had it down almost to a T there. Well, hey, thanks so much for talking about Smith charts.
Sure.
Ooh, I'm interested in it. I need to learn a lot more about it, but I don't know.
All right.
I might just hook the capacitor and inductor up and play with it, without looking at the chart. I don't know, but
Okay.
I don't know.
Got a number of videos on my channel too. You can give everybody your YouTube channel again so they can watch you the videos. Sure. Yeah. So it's just go to youtube.com/W2AEW, and that'll bring you to my YouTube channel. If you just put in the little search bar there, Smith charts, you'll see I've got probably a half a dozen videos on the Smith chart. One of them, it does exactly what you say. Is actually I show the Smith chart on a network analyzer.
Uh-huh.
I hook up a big, roller inductor and capacitor network to it, and you can actually see moving around the complex of the chart by just turning those dials. So very visually.
And someday I need to get this VNA out again and start using it. I bought it and I haven't even used it yet. We had a little talk on it the first night. I think you came on the show, and I need to figure out how to use it. I got so many things I want to do though.
I think it looks like Ron wins the internet with the best joke, saying if you get a horseshoe-shaped trace on your Smith chart, is it a blacksmith chart?
Yeah, it could be.
With that one, Ron. That's good.
Yeah. Well, look, hey man, thank you for sharing that. Hey, we had I think Bill Brown joined us. Bill, are you in there? Bill Brown. Bill
Yes.
joined us. Yeah, I think he's in there. There he is. Hey, Bill, how you doing, man?
I'm doing good.
Did you understand all that Alan talked about? I mean, you're a NASA guy, so you probably can comprehend most of that, right?
Yeah.
Well, good.
It was a good explanation and I really enjoyed it.
Well, great. All right. Well, Alan, again, thank you for doing that. I don't know what you're going to have next week. Think of something for us next week and come back and surprise us again.
Yeah, I think I got a cool idea for next week.
Okay. What's the idea? Are you you want to not tell us, or?
I'll give you the hint, because one of the more popular videos I had, it was on making a time domain reflectometer to measure the length of coax. But I got an even easier way where you don't even have to build a circuit. So as long as you've got a digital scope, I can show you how to do it really easy.
Oh yeah. Well, won't some of these antenna analyzers do that?
They will, but if you don't have that, or you want to just learn things, do things a different way, and have fun with your equipment and spin knobs
And that will measure the length of the coax?
Measure the length of the coax with nothing but, if you have a digital scope and a 9-volt battery, you can do it.
Oh, that's cool. Will it show you any faults in that? Let's say it says the coax is 100 feet long. Will it show you any faults, like a tear or anything in the...
It can. It certainly can. It can show you distance to some kind of a fault. Sometimes the fault isn't open, so it looks like the end of the cable, or the fault might be a short or something like that. But so you can kind of get there. So
that'd be cool.
Kind of very rudimentary, but it's a simple thing that you can go ahead and go play.
Okay, well, cool. Looking forward to that. All right. So, hey, let's see, Glenn. Real quick, Glenn. I don't want to keep you to the end of the show and not give you an opportunity, man. What do you got going, Glenn? Anything special out there?
Not really. Got word today, confirmation today that the review I did on the Dr. Duino Explorer board is going to be in the January issue of QST that should be out any day now. And that's kind of like an Arduino development system on a single board, and it's really handy.
I've been seeing that Dr. Duino thing advertised in a lot of places.
Yeah, it's really popular. The Pioneer that I reviewed, what was that, October, November, thereabouts? It's more of an introductory starter system, whereas the Explorer is more of a prototyping and development system.
Yeah.
And I actually used it for several projects in the new book.
Okay.
But no, outside of that, I mean, I'm just busting my tail on the book, getting real close to the end. And once that happens, I want to start playing and getting back on the air.
Okay. Well, you know, I've got a lot of things I want to do around here too, but I don't think I'm gonna have time to do all of them. I need to get you. I need to get you up here one day. Yeah, I need to get you up here one day. Help me get my JT65 straightened out.
Sure.
You know, I want to get JT65 on the show here as a segment on the show. I want to do some EME, some moon bounce. Now, I don't know. It's possible to do moon bounce with some relatively small stations, especially if you're talking to a high power station. But you know, a single Yagi, maybe 70 to 100 watts in digital like JT65, it's possible, and that's just what I want to do. You know, I talked to Martin this week and to see if he can round me up an amplifier. I need a little bit of power for the JT65 on 440. I like to run about 100 watts. The what?
I was going to say, I've got a 2 meter 160 watt amp, but I don't have anything for 440.
Yeah. So, well, let me ask you a quick question. Do you think 2 meters would be a better place to try EME or 440?
Oh, I think 440.
440. It's really all about the gain, right?
Yeah.
So you really get the gain. I mean, that's I could chat a little bit about what we did for Diana, which was the extreme case. But actually, you know what? Let me do this again.
Well, when you talk about the gain, I mean, I've got a single out on my azimuth elevation. I've got a single UHF Yagi and a single 13 element VHF. I mean, I don't have a stacked arrays or anything.
No. Like I said, you really want to get as much gain as you can, especially on the receive end, because. But just to give you an idea, this is what we used during the anniversary for Project Diana. It's a 60-foot dish,
right?
1.2 gig. So we had 46 dB of gain, which gave us an effective just under 8 megawatts of effective power. We were getting S9 plus signals reflected off the moon. Is pretty amazing. So
I know
you're not going to go that extreme.
I've had dishes in my yard before, but I don't think I can get anything that big out there. Yeah.
No, this was
you're thinking
at that site.
So you're thinking 440 is my best band. Now, again, a single Yagi, maybe 100 watts. I don't know what I can get. I can't get a whole lot of power.
Yeah, but you can get that gain because you can build a 15 element 430 beam, out of coat hangers.
Yeah, because the same amount of gain for 2 meters would be an antenna that would be 4 times as big. So.
I visited the W5UN, Dave Latchkey's station in Texas, and he had a 2 meter array that was larger than his house, and he actually had a Jeep that would push the Jeep body with the differential was an electric motor. So this little Jeep moved this whole array around in a circle, and it was just a monster array. So you probably are better off as far as size versus gain on the 70 centimeter band.
Yeah.
Now there was a fellow in I think it was KB8RQ had a super EME station up in Ohio, and he passed away. And I understand some of his antennas. I don't know if they're still available, but I can put you in touch with somebody that
No,
recently disassembled that.
I don't think I want to put any more. I want to try it on what I've got. I know I'm trying to do it on the low end, and it can be done. It can be difficult. But my understanding is there's people out there 70 to 100 watts with JT65 making contacts. Now, I think you got to make a contact pretty much with the big guns at the other end, but it's possible. I just want to make a contact bouncing a signal off the moon. That's all.
Yeah, the modes like JT65 help tremendously because they're very narrow bandwidth, and you get all the processing gain on the receive end that you can decode signals that you can't hear.
So I'm looking at my WSJTX. It has JT65 in it, but I can't find any A or B. Where do I find it? Is that a different download somewhere? I mean,
Not me.
Yeah. I've never operated any of those modes, but I would imagine you can.
I mean, it's JT65. It's JT65, but my understanding is A is for like 2 meters or whatever.
Okay.
B is for UHF. It's been made better for UHF. I guess it's plain old JT65 is HF, but where do I find it? It said be sure to use the one out of the WSJTX suite, and I got the suite, but all that's in it is JT65. What do you know, Glenn? Do you know anything, Glenn?
You caught me Googling. No, most everything I've done is JT65B.
Okay. Well,
Looking up right now to see. I used to know the difference.
The suite that I've got here does not have A or B in it. It just says JT65, and I don't see anywhere to select that particular one. My understanding is A is built better for like maybe 6 meters, and I'm not sure about 2, but the B is specified particularly for 440, maybe 2 meters and 440. I don't know.
Okay, basically the only thing they differ in the frequency shifts between the 65 tones. For 65A, the shift is 2.7 hertz. For B, it's 5.4 hertz. And for C, it's 10.8 hertz.
Okay, well,
basically,
again, my reading says I need to use JT65B, so I guess I'm gonna have to download it. And it said don't get it from some other place. Make sure it's the genuine JT65B, I guess from Taylor.
Well, see, JT65B is for 2 meters, and it's saying B or C are for the higher bands.
B or C.
Yeah.
But if the EME community is kind of decided upon a particular one, like JT65B, then that's what you want to use, regardless, whatever band you're operating on. But I would even if you go to Joe Taylor's page on this, just Google WSJ.
I just brought up WSJT-X, and when you go to JT65, it defaults to A. In the bottom left-hand corner, it'll say J.
Oh, really? Okay. So maybe I just am not aware. So there isn't
A, but I don't see how to change it to B or C.
Yeah. Okay. All right. Well, I'll need to look at that.
I'll say JT65A right on the bottom of the screen.
Okay. I didn't realize that was there. Of course, I'm kind of new with it, so.
Yeah, and there may be an option on that screen, since it's only a difference in the frequency shift between tones. That may be a sub option once you start the JT65 screen.
Yeah. Wow.
I mean,
okay.
I'm looking to see if there's a way to change it.
Well, okay, so
Oh, it's probably based on the band. So let me put it up there on 70 centimeters and see if it just changes it.
yeah, maybe it does.
No, it didn't.
No. Okay, Bruce in the chat room has sent me a link here. I'll check it out a little later. Thank you, Bruce. All right. Okay, guys. Well, anyway, that's what I want to do coming up here soon. Now, let me jump into an update on our balloon. For the guys that were following Dash 20, you saw it got stuck in the Philippines. What happened was, as it was after it left China, it was instructed to take the fork when it hit the fork to take the fork, and they took the wrong one, so it went down to the Philippines and stayed down there for a while. So anyway, we finally went down in the Philippines. I got a picture here that a guy sent me that is down there. He's a diver, and we got this picture here just came in yesterday, I think, and if you look real closely, you can see W5KB-20 right there. I don't know. I doubt it'll ever be recovered. But anyway, we are planning. I'm planning. Bill probably maybe hadn't noticed it, hadn't heard it yet. We'll get Dash 22 off this Saturday morning. If the weather's good, we may get Dash 22 off. And this is not the super duper high altitude. We're having a little trouble with material. It seems that we got to find some really good gas barrier material, and so we're having trouble there. So this will be just a standard flight, 46,000, 45,000. We might get 46. I don't know. This tracker is lighter than the last one. I think Bill, the total weight on this one's going to be about 10 grams total. I think the one we flew last week was 15 or more, probably about 15, but this is going to be 10. So you think we might be able to hit 46, Bill? What do you think?
You might, with a 10-gram payload, you might be able to do that. So, but what happened to the other day is it picked up ice, and once you pick up some ice on the balloon enough to cause it to come down in altitude, then it hit the freezing level and it started to melt off. But there were so many clouds, and it just hopped up and down like a roller coaster all day.
Yeah. And
all the ice didn't melt off the balloon. So at central heating, it probably just came right on down. But it tried all day long. It was bouncing around 11,000 to 20,000 feet.
Yeah, and we saw that. We saw that happen.
Exactly like a roller coaster.
Yeah, we saw the same thing happen to the one that crashed in North Carolina. It got ice and it went up and down, And hey, somebody sent me a suggestion: put Rain-X on the balloon, man. What do you think? Rain-X, keep that moisture off of it, or
yeah, maybe Teflon.
Yeah. Well, we just got to be higher than it. I don't know.
I saw you testing today. I saw you testing your next balloon transmitter. I saw it being tested. Noticed that on Whisper.
Yeah, it's on. It's been on a couple of days. I've got to mount it and get it a final package together, and it's going to be lighter, much lighter than the other one. In fact, here's the base for it right here. Let me show you what we got here. We're going back down to 6 panels, 6 solar cells. And looks like our styrofoam here is about, I don't know, maybe 5/16 of an inch thick. I mean, this is so light. I cannot find anything lighter than styrofoam. I have weighed so much stuff. And people said, well, hey, get one of these carry-out, the styrofoam carry-out things, that's real thin. Well, I brought one home and I cut a piece of it out. And that little thin piece of styrofoam weighs 5 times what this piece weighs. I mean, this thing here almost floats. I almost have to tie this down, Bill, keep it from floating away. So the tracker's going to go on here, and we're going to put the tracker right in the center. I'll probably just cut a little slot in it and glue it in, and then I'm going to run 2 supercapacitors on it. Bill, I was only running 1 supercapacitor on the other one. I told you I put it across the 3-volt side. I had 3-volt capacitors and took a chance, and I'd already run it for about a month at that voltage, and it didn't explode, so we took a chance. But hey, the styrofoam right here, the styrofoam and the 6 solar panels comes in at 3.6 grams. That's all. The tracker is about, I don't know, 1.8 grams. The heaviest thing is going to be our super caps. 2 of them are going to run about, they're 1.35 grams each, so they're going to run us about 2.6 grams. So total weight.
I found a super cap combo that has the resistors in them.
Yeah.
That weighs 144 grams.
144. And what's the value of it?
It'll give you half a farad.
A half? Yeah. Well, yeah.
They're 1 farad super caps, and
yeah,
they're combined.
I'd like to order. I'd like to try some of those. But I can put these 3 farad capacitors on here, Bill. Charge it, and take the voltage off, and it will run a solid 2 minutes on those capacitors. And that would be two of them in series is 2 3s in series would be 1.5 farad. So I'm just wondering what a half farad would do. A half farad might run it 40 seconds maybe.
It'll charge up quicker in the morning.
Yeah.
And I've had good luck with a half farad. So and we're talking. Yeah. Just 10 or 20 years ago, something that was 1 farad or 3 farads would probably be as big as my kitchen table and weigh 20 pounds. So it's just amazing, these supercapacitors, just how lightweight they are.
Yeah. Well, our friend Edward, he flies this without any supercapacitor at all. But right. I'm thinking, the theory is that this thing is floating with the wind in the balloon, and everything is just very still. But I think, here's my theory, I think this sucker's doing this out there in the wind. I really do. Do you think it's moving around, Bill? Or do you think it's just...
Once it's at float altitude, it's probably not, it probably is a slow spin in the...
Slow movements? Well, see, the reason I
don't think it's doing a lot of pendulum action unless you're into some severe turbulence.
Yeah. Well, I'm sure that different winds probably merge up there, but what I'm thinking is, without a supercapacitor on here at all, there are going to be times the sucker may point back a little bit, and it's going to lose the sun. And if it loses the sun, it goes off. It has to start back up again. It resets, right? But if we got a supercapacitor on there and it goes out of the sun for 4 seconds, 10 seconds, we'll keep going. So we're gonna run the supercapacitors on it this time. And since I'm not
what's the max voltage that you can get out of that array? You're only running 6. The max voltage is going to be about 3 volts.
Well, yeah, I measured it outside. It's a little bit higher than that. In the bright sun, it's about 3.6 or 3.7.
Under load?
Well, no, not under load. But
well, you'll probably be down.
Well, I need to do some more measurements on that. So, if I thought we would only have 3 volts here, I'd only run 1 super cap on there, a 3-volt super cap. But I'm afraid that I might be pushing it a little too much with just a single 3-volt on there. What do you think?
Yeah, and the colder temperatures, your solar cells are going to be more efficient, and so you're going to have a higher voltage. I saw that in the flight today that was launched in Pella, Iowa. WB0URW flew one of my whisper boards, and you can see that the solar panel on the way up, where you're getting a lot of airflow over it, and it's very cold. Actually went up to about 5 volts or more. And then once it got to float altitude and you no longer had that airflow over the solar panels, the voltage went down to about 4.7 volts. So you actually lost about, you actually gained about a half volt just from the cold temperatures. And it's still, though, the ambient temperature just floating there, you're just going to see maybe 10 or 20% increase from what you're measuring on the ground.
Well, you know, I'm not running any voltage regulator at all on this one. I've decided not to, because with the number of cells, I'm keeping the voltage
Yeah, you
low.
wouldn't be able to do it with just 6 cells.
So I've no regulator. Also, I've taken that reset switch off this. You know, the other ones have been resetting it. And I looked that up. They were resetting at 2.53 volts, I think. And with the reset switch off, I did a little testing here, and it looks like it will transmit down to about 1.9 volts. So with the reset switch completely removed and just these cells, I should get a little over 3 volts down to maybe, 1.9. It maybe will operate. So we're gonna try that. Somebody said I should put my email on the bottom. I don't think I'm going to do that because what's the saying? If there was no such thing as bad luck, I wouldn't have any luck at all. I'd be afraid this sucker would come down somewhere, and as heavy as it is, 3 grams, poke somebody in the eye on the way down, and that would be probably one of the biggest lawsuits in the country. And I think we had one go down on a Russian, or somebody had one went down on a Russian army base in, I don't know, over in Eastern Europe or something. I don't know if I want my name on it or not, Bill.
Do you have any enemies, Tom?
Now, I was thinking I could put Glenn Puppel's name on here, man, and his call letter. And then if somebody contacted him, he could let me know.
Yeah. I have gotten a number of them back, but not not from another country. If they land in the United States, I've been about 10% recovery on these, just by using my backup recovery system, which is my email taped underneath the solar panels.
Yeah. Well, somebody said, why don't I just burn $100 bills for entertainment? Well, that's kind of what we're doing here. We're building our own tracker now to hold costs down, and I think we've done really well in doing that. But, typical launch of, especially if you're using SBS, you're looking at $250 a launch, and that's just like tying $250 on the end of that string on that balloon and letting it go. But, Bill, it's got a lot of fun, man. Yeah,
you got the fun of building it and everything else and tracking it. Come on.
Look at the fun you have, man. Look at the. Hey, you make it across a war-torn country and it didn't get shot down. It just every day there's something new about it.
And you might cross the equator this time.
I was really hoping that we were going to cross the equator
really close
and fly. I saw we were within about 1 degree, and of course, nighttime came. I don't know how close we came to it. Who knows? But that was pretty close, and I really was hoping that we would fly the rest of the flight in the southern hemisphere, but that didn't happen. So anyway, it's fun. We've got a few. Well, I just ordered 15 more boards, Bill.
Yeah, I have a couple. Said about something for the balloons that you've flown, Tom, and then maybe the same question to you, Bill, since you're involved with a lot of other balloons besides Tom, is what's the longest distance that you've gone? And I think, we're probably, 2-3 times around or whatever. But I guess another interesting one is what's the longest flight time? Even though you might get stuck somewhere or whatever, what's the longest one's been up?
Hey, Bill, Bill, didn't one of the balloons make it 735 days? Was that an SBS?
Right. There was a flight by W7QO that he sent a balloon that stayed up over a year.
Wow.
And he went around the world 33 times.
Wow.
My personal best is almost 3 months, and I went around the world 6.5 times. But I ended up, my last lap ended up crossing the equator, and there are a lot of big storms in the equator, so there are higher cloud tops, and so I got hit by a big storm off the Ivory Coast of Africa on that one. But just a few recent, there's 3 balloons up currently that have been around the world twice. One of which actually is 1.8. It's supposed to cross the second lap here tomorrow. It was launched by a school in Pella, Iowa. And they have 2 or 3 balloons up right now, 2 balloons. One that they just launched today on Whisper, and the other one was an APRS balloon.
And Alan, the biggest problem we have are, I think, the storms. And we've gone over a bunch of storms, but the smaller, cheaper, inexpensive balloons, they're going to fly low. Bill, what 30,000? Will they go a little higher? 36 maybe?
If you put 2 party balloons together, the 36-inch variety, you can, with hydrogen, you can probably get up near 36,000 feet. Yeah. Which greatly increases your odds of making it around the world. But when you get above 40,000 feet, that once again increases your odds of making it around the world, which is those more expensive SBS balloons.
Yeah, exactly. And that's why we've been going all our flights with the bigger, expensive balloon, because we're trying to go for the long duration and trying to, it takes luck.
Icing is always a problem. If you hit the cloud tops and build up enough ice, it's hard to shed that ice off. And once you start coming down with a lot of ice, it's hard to recover from that. It has happened, but you're likely to come on down. So that's one of the biggest issues. Is icing. And
we in that last flight we had, we were in some clouds that were 50,000 feet, and our maximum altitude was 45. Hey, here's the guy that went down. This is the guy that went down in the Philippines right here. He looks kind of chopped up. That's because I operated on him about 3 or 4 times before we actually flew him. But this is the one that crashed in the Philippines. We were trying to break our record of 3 times around in 72 days, but that's what we're going to try on this next one. And let's see. That's the one here that crashed. And let's see what we got here. Oh, and you can see the different winds right there. There's a shot there. It seems like this last flight we were picking winds of like 4 miles an hour a lot of times. I don't know if this is over. This may be over.
That's at Kermit House in Memphis.
Is that here? That's here. We looked like we were never going to get out of here, but if you look just north of us, there's 119 mile an hour winds. So. We just had bad luck on this last flight, and I think that if we launch again, maybe we'll get in that jet stream. We've flown as fast as 140 miles an hour, and hopefully we'll do better this next flight. And
the highest ground speed I've seen on one of these Pico balloons is over 230 miles an hour during the peak of the winter. January and February are your highest winds in the jet stream.
Yeah. Well, we're hoping to do that, and we're hoping that in about a week, this little guy right here is sailing at about 200 miles an hour across. We had one that went across the Atlantic in just like record time, man. About a day it made it. It really surprised us. But then I think that's the one that took a vacation in Burma, and then it took a longer vacation in the Philippines. But anyway, we hope to get it off. If the weather's good, we'll launch this weekend, and we expect it's going to fly around 46,000. That's the most we can get, guys. You just can't get any higher. I don't know. The balloon gods just won't let them go any higher, man. That's it.
With existing balloons.
With
If you make your own and make it a little bigger, you'll go higher. But
yeah. But and you know, I mean, I've played with all kinds of material. I can make one that has a lot more capacity. The problem is the membrane of the balloon. It's going to leak out the hydrogen, and it's going to come down. You know, I mean, I need something that stays up for months. You know, that holds it. So, Bill, I'm looking at all types of gas barrier plastics and multi-layer stuff, and most of the stuff's coming out of Japan. And you go on our website and you try to make an inquiry, you got to almost have a degree in I don't know what to even fill out their inquiry page. You know, their email, contact us. You know, oh man, really complicated. But it's a lot of fun, and our next balloon will be the SBS. We're going for the high altitude. We've got some of the smaller balloons here, the little silver balloons, like Bill's talking about, and also the small 36-inch clear. We can fly them, but you know, they're going to fly at 30,000 feet, and we don't have any way to steer them around the storms. We're going to be flying right through storms. Well, Bill, shoot me a link about that. Shoot me a link. I'd like to experiment with one of those point.
I'll put one in the mail to you.
Yeah, 0.4 farad capacitors. Also, I'm still waiting on all the parts to build the new tracker. I haven't got a single part in yet. I don't know what's going on with AliExpress out there, man. I guess they're trying to counterfeit some up real quick before they send them to me. I don't know.
But, you know, it's funny. It comes fast and slow with them. Sometimes I'll order something and I'll get it next week, and I'll order something, you know, same thing from the same place, and it's 6 weeks.
Yeah.
So.
Well, I've had stuff on order now probably about a month, and I haven't seen it yet. All the GPS modules and the little Arduino, the 328P chips and stuff, and I hope the quality is good from AliExpress. I hope it works.
Oh yeah, they're one of the better ones, but
all right.
You know, a 328P is a 328P. They all come from the same place now.
Well, is it the same? What if it's just counterfeited out of China and it's just a square piece of black with 32 leads sticking out of it?
Well, it works.
You know. Oh man.
You know, I mean, I hate to say it, but, you know, chips like that are a commodity these days, and it really doesn't matter whose fab shop makes them. It's the same thing.
Yeah.
It's not like the old days where you were really fussy about components. I mean, one of my first jobs was quality control with a modem manufacturer. We actually tested each chip that came in to make sure that it was working, and we had like a 5% failure rate.
Yeah. Well, look at here, Bill. I want to show you something, man. You probably don't have one of these, not like this anyway. Let me show you what I got here, man. Look at this. You see that?
Oh, that's a.
You see that right there?
Like a pogo plug.
I put me a pogo deal on it. I cut me this a big clothespin out. Put me a pogo thing on there. And for people who are wondering what that is, if you look at this, is one of the little new tracker boards that we're going to start building. And down on this end here, you can see 6 little holes on that end, and that's to program it. And the programming cable will hook to these pogo terminals, whatever you call it, and they're spring loaded, and and you just set it on that board. You just set it on the board like that right there, and program the board. And then when you get through, you just open it up, take the board out, and it's programmed. So
I have a similar thing that goes into the programmer, and it's got little pogo plugs on the end. And so all I do on the circuit board is I have 6 little pads and 3 guide holes, and it's no bigger than a small couple of resistors. And there's weight, but since there's no header, and that works great. I just push the pogo plug on it, program it, pull it off and off, and it's ready. And then they have a little clip on mine that will hold the pogo plug on if I want to do a whole bunch of mods and programming for a while. But for just a one-off, real quick update, I just push it on and away and program it.
So this is going to be our new tracker board, and you can see the GPS goes here, and the Arduino 328P is going to go here. After we program it, we break this off. You can see it's got a little breaking point there, and we'll break that off once it's working right, and that'll take some of the weight away. And as Bill says in all his presentations, you got to make this as light as you can, and then make it lighter?
Yeah.
Make it even lighter. So
make it as lightweight as humanly possible, and then make it lighter.
Yeah. So Bill,
that's the real challenge.
I'm going to be going
designing these lightweight.
The problem, I'm going to go a little heavier with this new board, because this is the one I've been building here. And, I had these boards made at OSH Park. That's the one. And this is the new one here. You can see this board's it's a little bit bigger.
Resistors, so
it's a little bigger.
It'll be a little easier to solder.
But this one, the parts are spread out a little bit more. And actually, there's almost no parts on here. I think there's a couple resistors, that's it. Plus, I think they're the 604 size, whereas this thing here is just really tough.
0603.
And Bill, the thing I found, it seemed like the hardest thing.
You have
the hardest thing I found, Bill, is I thought, the 328P, the 32 pins on there, I think, and that's going to be tough. But that's probably one of the easiest ones to put on. I have found that little SI 5351, that's about the size of a tick, and it's got 10 leads on it. That's the tough one. And man, I have a little trouble with it.
And it's hard to hand solder 0402 resistor components. 0603 is real easy.
Yeah, and this one will hold the 603.
That'll make it a lot easier to assemble.
And these are, I tell you, when you look at these, Bill, they're almost identical schematics. It's just that
there's nothing to them.
It's nothing to it. And
I don't know, is there an output filter on the other one?
No, there's not, and there's no filter on either. So this one has about 15 parts on it, and this one has 8 parts on it. And, like bypass capacitors, there's a bunch of them on here, the little 402s, they're little. There's almost none on this one at all. And he says he hadn't had any problems with needing the bypasses on there or anything. But I'm going to try it and see the parts spread out a little bit more. You can take 603 parts, and I think they'll be easier to build. It'll be easy to program.
Bypass capacitors, and particularly when there's RF involved.
Yeah, it'll be easy to program with the pogo thing here, where I solder the leads on here, And then if I take the leads off, if I want to redo it, I have to solder the leads back on. And so anyway, that's kind of what we got going here. All right, let me just make a quick announcement here on WBCQ. If you're out there listening on shortwave, we'd love to hear from you. If you're out there on 7490 WBCQ out of Monticello, Maine, you're listening to Amateur Radio Roundtable now. This show's about ham radio. In the last 15 or 20 minutes, we've been talking about some little simple balloons that we've been launching that are going around the world, and they track back to us by ham radio where we can see where they are. But if you're out there on WBCQ, send us an email to Tom at w5kub.com, Tom at w5kub.com, and we'd love to hear from you. You can also watch this show if you're interested. You can watch this show on Tuesday nights, 9 p.m. Eastern Time on w5kub.com. Now, somebody corrected me in the chat room earlier about the UTC time. I thought we just changed, didn't we change our time by an hour here recently? And Bill, aren't we, we're only 5 hours difference right now in UTC.
We're 6 hours.
Are we 6 hours now?
6 hours.
Okay, we're 6 hours. Okay.
We were 5.
I went the wrong way. Yeah. How does he know which way we're going? How does he know where we're going, right? That's from a movie, if anybody knows what movie that is.
I just look at my cell phone and let it tell me what time it is.
So yeah, okay. So the show is at 0200 Wednesday UTC, 0200 UTC Wednesdays. And you can watch the show if you go to W5KUB. And I wish that we would quit doing this daylight savings and flip back and forth time. I mean, man, right now it gets dark here like at 4 o'clock, and by 9 o'clock, I'm going crazy here. It's so dark out there, and I never can get the UTC right. Just like then, I got it backwards, and it's hard for me to publish it somewhere. Like we have some ads out there with the time on there, but you can't just say UTC is 6 hours from November to this month or 5 hours from here to here, because it happens in the middle of a month. It happens on different days. So, man, it's a mess.
I wish they'd just pick a time and leave it.
Yeah, that would be cool.
By the way, I've got a little bit of an answer on your JT65 question.
Yeah.
I followed that link that was posted, and it looks like on the JT65 menu, you have a sub mode menu option.
Okay, I'll have to look at that. I have not found it yet.
And that's
where
I saw
you
that
there too, Glenn. Yeah,
I'll look at that.
Yeah, that link is good. It brings you kind of the usage guide into one spot. And it says a sub mode equal B for 2 meters 440. So.
Okay. Yeah. Well, that's what I need to use then, because it's going to be tough, but we're going to try it.
I think it can be done.
I looked out the window tonight, and two, I'm going to have to do it because where my antennas are, the house is going to block it to the west. But I'm looking out to the east tonight, and the moon is really nice and full and bright out there tonight to the east, and this would be a good night to try it. I also understand that the best time to work moon bounce is right when the moon is right at the horizon. Have you guys heard about that or read about that? Somehow the Earth gives a signal a better pathway to the moon instead of it up, very high.
Well, if you think about it, as the moon's just rising, it's much larger than it is when it's overhead. So you do have a lens type of effect.
Well, I don't know.
Yeah, it visually looks larger, which means, like I said, that you are getting some magnification, if you will.
Well, I don't know that it's magnification. I think it has something to do. I mean, ducting is not the right word, but there's some type of physical properties where the signal traveling more toward the horizon, near the horizon, is better than with it up in the air. Glenn, you can research that and report on it next week.
Can I just take the demerits now?
Yeah, you can. Yeah.
Yeah, when we were doing that Project Diana, the beam width, because we were running 1.2 gig on a 60-foot dish,
Yeah.
the beam was just over 1 degree. So we literally had to be actively tracking the moon because it was because the moon moves like a degree and a half a second or so, or degree and a half a minute or something like that. So we actually had to be actively tracking the moon with.
Well, I think my antennas are going to be a little bit more broader than that. So
It should be.
yeah, and I'm hoping because hey, I think to carry on a JT65 contact, I think it takes like 7 minutes total.
Yeah,
Okay.
it's 40-something seconds per transmission.
Yeah, it's about 7 minutes. So it could.
We had an event with Arecibo, had a 400-watt transmitter into the Arecibo dish on the 70 centimeter band, and we, our local university here, University of Alabama, Huntsville, their radio club had a single 70 centimeter Yagi with a mass mounted preamp, and we were able to hear them on sidebands.
Wow.
JT65s was about S9, and sideband was just sounded like a 20-meter pileup, and it's just incredible. So it is possible to do with a single Yagi, but it takes a mega station on the other end. But there are a number of super stations on the EME that you can set a schedule up and with a single boom.
The longer your antenna, let's take a 2 meter Yagi. The longer it is doesn't necessarily mean you're getting a lot more gain. But I mean, there's some point where you keep adding elements. I don't know. You're just not getting the gain.
Well, you reach a point of diminishing returns. That's when you start stacking multiple beams.
So I saw some construction of a 2 meter beam. You guys may have seen this, where out in the forest, whatever, they run like a couple ropes, and they put elements across the ropes, and they can make that antenna, that beam, 500 feet long. Mm-hmm. Of course, it sags, so the rope sags a little bit. And I was looking at pictures of it, and you can see it sagging there. But people have actually built long antennas, long Yagis, using a rope like that.
Rhombic is also something you might consider. I built a rhombic when I was in high school on 70 centimeters, and it worked pretty well.
Yeah.
Yeah, and by the way, they're talking about it in the chat room, but have you all heard that the control unit that was suspended by cables over Arecibo came down as well?
Yeah.
The cables snapped. So it's gone. They were going to do controlled demolition on it.
I heard that they were going to demolish Arecibo.
Yeah.
Well, it came down before they got to demolishing it. It came down on its own.
Yeah, it's demolishing itself right now.
That's a shame. I was out there, 1978, 79. Yeah, got to see it in all its glory.
Yeah, well, you got to see it. That's cool.
Yeah, I got the cook's tour of it.
Yeah, I worked the guy who was at WP3R or whatever that's down there. I worked him on I think on 20 meters many years ago.
Yeah, it was a really a fascinating place to see how that dish was suspended in the valley.
Sure. Yeah.
Between the mountaintops.
Yeah, I think the best view I ever had of it was in the movie Contact.
Yes.
All right, guys. So what else do you want to talk about tonight? It's getting a little late. It's 10 o'clock.
Yeah. Yeah, it's probably about my bedtime.
Yeah, it's getting late on the East Coast, man.
Yeah.
Yeah.
Okay.
Yeah, those people have to go to work and stuff tomorrow.
Yeah, I got to come right back to this chair to go to work tomorrow.
Yeah.
I'm sitting in my office.
And you probably don't even have to get dressed to go to work, do you?
Well, at least from the waist up, I do.
Oh, yeah, that's true with Zoom now and everything. Yeah. All right, guys. Hey, enjoyed it tonight.
All right.
Thanks everybody for being with us.
Absolutely.
And we will talk to you later.
All right. We will see you all next week.
All right. Sounds good. Good night, everybody. Good night, everybody on the show out there. Thank you for watching tonight.